in this lecture we're going to finish talking about Introduction to Programming, but we're going to focus on the hardware and the digital aspects of the software. So a computer you can define as a machine that manipulates data and carries out a set of instructions. Remember, it takes input, has to do some kind of processing, and produces output. That is what computation or a computer is. And so the machine aspect in this definition you can equate to being the hardware, and the set of instructions is the software. Now we have three pieces of really important hardware, and the first piece is our central processing unit, and this is our brains of the computer, and it contains registers, and there are other registers located close to it, but we're going to put registers right here in this category because they're little tiny pieces of storage, and they're really quick access for the processing unit. And you can think of as where we store information, the closer it is to the CPU, the faster it is for retrieval and for storage. So there are registers living there, and then we have the random access memory, and this is where your running programs live. Okay, and this is closer to your CPU, and your program, when you start it up and run it, lives in RAM, and it will load data into registers as it needs to. And then you have the hard drive where your programs and files are stored. Okay? And then that's even slower to access. So what is software? Software is any kind of program, computer program. We have one primary piece of software that lives on the computer, and what would you say that is? It's our operating system. So what's its purpose on the computer? I would say to interface between the hardware and applications. Okay, so what are applications? Well, what I distinguish an application? This is a program that sits on top of OS. Okay? Now, what can every program, the operating system itself, right? So any application, operating system, anything, software is still boiled down to discrete numbers and circuits, more specifically, because that's where it all has to go. And you can think of circuits are always on, off, or open, close, right? But they're binary. They're 0 or 1. They're base 2. And so when we talk about base 2 numbers, then we're talking about whatever number that is how many numbers you can have in each placeholder. Or position, whatever you want to call it, right? Okay, and the number. So for a base 2, you get 2 numbers to choose from in each placeholder position, and those numbers to choose from are a 0 or a 1. And we always start with 0. We like 0. And so what number or what base do we use to count in? We use base 10, which is called decimal, right? And so what are our range of digits for each placeholder? We get 0 because we always start at 0, and we get 10 numbers in each placeholder because that's the base we're working in. And so 0 through 9 is what we get in each of those positions in our number, right? So each digit in our number can be a 0 through 9. Hexadecimal, which is base 16, okay, what is its range for each digit? Well, we start at 0, right? And so 0 to 15 would be how many numbers, because remember we get 16 numbers in each one of these positions. So 0 through 15, but whoops, this is problematic, right? And so what are we going to do about that? Well, we have to have only one thing in each of the placeholders or positions because we can't allow it to take up 2 positions. That would mean something different. And so here we go 0 through 9, and then we decide to use the alphabet and go A through F to be able to get something there in each one of those placeholders. What about with base 8? Octal. What do you get for each one here? 0 through 7, and that's your base 8. So how do we count decimal? I mean, we take it for granted. You just count your numbers, but you actually have a process by which you come up with that number being a decimal number. And so when you're told that you're given, let's say, 100 in base 10, then you know that this is 100 because you're saying 1 times 10 to the 2 plus 0 times 10 to the 1 plus 0 times 10 to the 0. And that's why we get that these are the ones, tens, hundreds, positions, right? Because of what we're using right here. We do the same exact thing with binary. And so when we say that we have 100 base 2, well then that means that we're saying 1 times 2 to the 2 plus 0 times 2 to the 1 plus 0 times 2 to the 0, which is giving us the number 4. In base 10. All right? And so let's do some more conversions back and forth between these two. Let's look at 32 here in base 10. All right? The number 32 is the number 32 because you have 3 in the tens position and you have 2 in the ones position. In base 2, we would express 32 as 1 with 5 zeros following it because 1 times 2 to the 5th is 32, and we don't need to add anything else to it to get that number 32. So how would we express 35 in base 10? Well, it's 35, right? How about in base 2? How many, we know we need 132, right? So I'll put an arrow here. We need 132. And then how many more do we need to make 35? We need 3 extra numbers to get to that 35. So how would we get 3 extra numbers? Well, we would need 1, 2, right? And we would need 1, 1. And that would give us the number 35 in base 10. So this is to the 4th. 0 times 2 to the 3rd plus 0 times 2 to the 2, and then plus 1 times 2 to the 1 plus 1 times 2 to the 0. So the number would be 1, 0, 0, 0, 1, 1. And that would be 35 written in base 2. How about in base 16? Well, that one's pretty easy. How many 16s do you need to get to 32? We need 2 of them, right? So we need 2 16s. And then how many more 1s do we need? We need 3. Right? And so 23 would be our number in base 16.